Michelle, question. Yes, after we finish this. So, um, let's just see where we've been so far. Okay. We found area between curves. We've done more difficult area between curves. Yesterday we practiced rotating um, areas around the x-axis. Today I just want to show you one rotating around the y-axis. Now I told you that we would also like to find volumes that have a a donut shape, so to speak, where you would have a hole in the middle. So we will start that on Monday. Today you want to practice this. I have 6 homework problems for you to do, but I can't remember what example we're on. We'll say examples. Okay, 5. Example 5. So this is how the book has the problem set up. I'll stay true to what the book says at this point. It says find the volume of the area bounded by these 3 equations, rotated around. In this case, now we're going to rotate around the y-axis. And so your first job is to be able to sketch an accurate graph of what's happening. And that's part of why I really like these problems. It brings back things that we did in pre-calculus and other times that are really, really, really important. So if we look at the curve y equals x to the third, that's going to look something like, say that. And then if I look at the line y equals 2, what kind of line is y equals 2? It is a horizontal line. And then how about x equals 0? That is a vertical line, and that would represent the y-axis. Very good. So now it's time to shade the appropriate region, or look at what we're exactly trying to find, what we're trying to rotate, really. And this is the shape. And what's different this time is we are going to take that, and we are going to rotate it. Oh, really? Nice job. Nice. And so we're going to rotate it now around the y-axis. And so if you do that, you'll get, that kind of shape. So that area spun around. Okay? Now, stay true to the method. All right? Do you remember what we do at this point? Let's slice it. I can't tell you how important it is to continue to think about that. We will slice a disc. We will get a disc off the top this time. And if we can find the area of that disc, then we can integrate it. We can do an infinite number of them. This disc also has a certain width. Let's quickly talk about the radius. Sammy, what is the shape that we cut off? It's a circle, and the area is equal to pi r squared. So I need to start by finding the area of that. Now, this is where it gets slightly complicated. As you look at the radius, before what we used to do, we said that the radius was often the distance from the x-axis to the height of the function. Is that the case anymore? No. As you can see, the radius is the length from here to here. Any ideas? Solve for x. Very good, Bryce DeBoer. Instead of y equals x to the third, I will take the cubed root of both sides, get x is equal to the cubed root of y. Okay, I'll try to, what Bryce is, yes, Bryce has the right idea. And this is the harder part is, how do we How do we state that? How do we say it? And here's the idea. Given any y value, we want to know what that length is right here. And so now we take that y value and it will output a certain x value. So put in this value, it will give us that value. So we got to do something that y value to give us that location this way. Whereas before we did the opposite direction. So you got to look at which way are you going. Now we're horizontally. So just like when we did area of curves, and we said, well, now we're drawing our rectangles horizontally. Well, when we slice a disc and the disc comes off, so our radius is now horizontal, that means that we have to have the equation solve for x in terms of y. And now notice, as you slice these off, you're not going to be slicing them off from left to right. You're going to be slicing them off from up to down, right? And we start at what value? Y equals 2. And we end at y equals 0. So you can see that everything is now going to be in terms of y. So what is my width? dy. My radius is equal to the cubed root of y. So that's what I have. Is there any confusion there before we move on? Because now I'm going to set up the integral. What we learned yesterday is that the integral from a to b, or volume is equal to the integral from a to b of the area of x dx. And so what I could do now is say that the volume is equal to the integral, we said, from 0 to 2 of the area, which is pi times my radius squared dy. There's got to be that point where you do that. You say, "Holy cow, that's cool." That's we had no idea that we would ever go down that road 6 months ago, but now we're here and we can do this relatively easily. Yep, this is cool stuff. So now we just need to integrate it. So setting up the integral is the difficult part. Actually evaluating it, not that bad. I'm going to rewrite it. Taylor Harris, what can I do with the pi? Take it out. 0, 2 of the cubed root of y squared would be y to the y to the 1/3 squared would be y to the 2/3. So we have pi times the integral from 0 to 2 of y to the 2/3 dy. So that's where I'm at. Now I take the antiderivative of y to the 2/3. What is the antiderivative of y to the 2/3? Y to the, we got to add 1, so 5/3 divided by 5/3 or multiplied by 3/5, evaluated at 0 and 2. Doesn't look like this is going to come out to be a very nice number. So we will take 2 to the 5 divided by 3 times 3 divided by 5. 1.9 pi, I guess we could leave it as. No. Can't do it. 1.9 pi. Okay, let's make sure that we understand where this came from, and let's talk about checking our answer, then we can move from there. So, boys and girls, true or false, you could type y into your calculator. No, but you could just substitute the variable for x and not change anything, and once you get to this spot right here, you guys know how to type this into your calculator, correct? So Boys and girls, you know how to check to see if a definite integral is evaluated correctly. What you don't know how to do is to check to see if you set up the problem correctly, and there really isn't a way to do that. So I have 6 problems for you to work on, and I'm going to really need your feedback throughout class if this is too hard or if we're ready to move on from it. Because where I'm at right now is on Monday, I would like to start integrating pieces like this. Okay, I would like to take a graph like this, and I would like to spin that around the x-axis. So that way we will have there will be a hole in the middle here. Then you will have more of a trombone shape, okay, however you want to call it. So I would like to move on to that. I need to know where we're at. Your assignment is page 391. Nope. Numbers 1 through 6. That gives you a half an hour to work on this. Some of you will honestly finish this assignment. The answer key is sitting up here. Please check your answers.